Notice, and this is typical copyright. We continue with mathematics syllabus for CSEC, which became effective in May-June 2018. As of January 2026, this syllabus has not been revised, but there are plans to change the structure of the exam from 2028 and onwards, with a few pilot projects now being conducted in a few Caribbean countries. The syllabus itself remains unchanged. The two main planned changes to the CSEC level math exam are: one, split the exam into two parts, and two, there will no longer be any alternative sections. All sections will be tested with compulsory questions. Schedule of videos, as you already know, sections 1, 2, and 3. All 51 of these videos have been published in their entirety on YouTube. Please make good use of them. Sections 4, 5, and 6. Some of these videos have been published on YouTube in their entirety, the others only partially. We are now at section 7, relations, functions, and graphs. This is the 26th of 26 videos, so really it is the last video from section 7, and I am running behind schedule. Of course, once we finish that, we'd have to go on to section 8, geometry and trigonometry, and then section 9, vectors and matrices. I am still hoping that by April, May 2026, I would be able to complete the syllabus. Please note this disclaimer down here. This schedule is just a projection, and it is not to be interpreted as a contract with anybody. Returning to section 1, number theory and computation. As I said, I have divided that into 33 videos, and they are all published on YouTube in their entirety, especially since this section forms the foundation on which the rest of the syllabus is based. Reminder down here, you need to know the times tables from 2 to 12, especially since calculators are not allowed in paper 1. Returning to section 1, some of these videos are even applicable in the primary schools. The students could look at them on their own. Teachers can use them in the inverted classroom, and parents can use them to help their children, especially for parents who think they don't know any math at all. For example, if you consider this box here, let me expand it to show you that section 1 really is primary school work. It says here, add, subtract, multiply, and divide whole numbers. That's video 6, whole numbers. And then video 7 says add, subtract, multiply, and divide decimals. And then video 8 talks about addition and subtraction of fractions. Video 9, multiplication and division of fractions, and so on. So many of these videos are applicable in the primary school from as low as grade 3, grades 4, and especially grades 5 and 6. So these videos in section 1 especially can be used in primary schools to help the students, to make life easier for the teachers, and to help the parents who think they don't have the math skills to help their children, even if it's just primary school. From section 2, consumer arithmetic, all 12 videos from this section are published on YouTube in their entirety. Section 3, sets, all 6 of these videos have been published on YouTube in their entirety. So as I said not so long ago, all videos from sections 1, 2, and 3 have been published in their entirety on YouTube. 51 such videos. Please make good use of them. From section 4, measurement. These videos that you see indicated in yellow here have been published on YouTube in their entirety. The others are only partially published on YouTube. If you need to have full access to those videos that are only partially published on YouTube, please see directions in the description below. Section 5, Statistics. Some of these videos have been published on YouTube in their entirety as indicated in yellow here. The others are only partially published on YouTube. Again, the same principle applies. Please see directions in the description below if you need full access to these videos that are only partially published on YouTube. Section Algebra, which seems to be a problem area for most learners. 7 of these videos have been published on YouTube in their entirety, and the others only partially. If you need to have full access to these videos that are only partially published on YouTube, please see directions in the description below. Section 7, this is what we are doing now. Well, about to finish. It has 26 videos, and this is the 26th video that we are doing right now. Before we go on, recall in the introductory video that I said you will need a good math textbook or maybe a set of 2, especially to get more practice questions. CSEC recommends these shown on the right here. From those, I would recommend these last 2 down here, as seen on the next slide, as they form a very good 2-volume set of math textbooks that is quite adequate for the current and the future proposed changes in the structure of the CSEC math examination. This is a picture of Volume 1, Mathematics, a Complete Course with CXC Questions by Raymond Tulsi, and this is a picture of Volume 2. Please note this disclaimer down here. I get no financial or other benefits from the sale of these books. Also, as of late 2024, a website with AI interactivity has been made available, free of cost, that deals with past CSEC math questions only, specifically from Paper 2. It is extremely important that you become familiar with how CSEC sets its questions for Paper 2 and what will be considered good or correct answers to such questions. This is the URL for that website. On the next slide, I will show you what the home page of that website looks like. This is the home page. You will have to register. But remember, I said it is free. This is that URL again. It will be in the description of this video below, so you can easily click on it and be redirected to this website. Another reminder that this formula sheet is provided for CSEC math examination papers. This formula sheet, it is included in the syllabus. If you don't have a full copy of the syllabus, there will be a link in the description below from where this formula sheet can be downloaded. This is the top part of that formula sheet, so you could see it a little better. I am going to state the obvious here, the obvious. You do not need to memorize these formulae on this formula sheet, as this sheet will be provided during the math examination papers. And this is the below part of that same formula sheet. While you do not need to memorize these formulae, you do need to know when and how to use them. So relations, functions, and graphs, as I said, we have finished almost all the objectives here, so I'm just going to scroll through this very quickly. All objectives here completed, all objectives there, 17, 20, 22, all completed. Well, we are now here, 23 to 25 have been completed. So we are at this last one here, 26. So we are here, objective 26, video 26. 25 objectives and videos have been completed from this section. These have been published in their entirety so far, 8 of them. Please make good use of them. And of course, if you need full access to those that are only partially published, see directions in the description below. When this video 26 is finished, it will be published in its entirety. So we are here, objective 26, last objective in this section. And it says, solve problems involving graphs of linear and nonlinear functions. That's this. Now, this seems to be redundant because that is what we have been doing all along the line. And as I said, you may now be thinking, didn't we cover this already in this section and in section 6, algebra? And you may be correct. So this video may just be a review of those related objectives. Of course, if you didn't have full access to those videos, then I will review some of these and you will have full access to this particular video. First of all, we will look at one example of linear functions, equalities, like solve two simultaneous linear equations graphically. Then we will look at one example of a linear and a quadratic function, solve those. Third, we will look at linear functions, actually in this case inequalities, solve two linear inequalities graphically. Then we will look at a fourth example, linear programming, which we have seen before. And finally, fifth, speed time graph, a variation of what we have seen before. As I said, we will review 5 examples of each type shown here, similar or identical to what you have seen before if you had access to the full videos. So, first example, linear functions, equalities, and we are going to solve two simultaneous linear equations graphically. But we will look at a variation of that. Solve, and this was what we did then. Solve a pair of simultaneous linear equations in two unknowns graphically. So to solve simultaneous linear equations graphically, you plot both equations on the same coordinate plane and find the point where the two lines intersect. The coordinate x, y of this intersection point is the solution to the system of equations, as that point will meet the requirements of both equations. That will be the x value and that will be the y value. So this is example 1. In this video, I think of two numbers, x and y. If I subtract twice x from y, I get -5. If I subtract 7 from y, I get -x. Using graphs, what were the two numbers I thought of? Now remember, there are different ways of solving this, but this objective specifically says using graphs. So we derive two equations. The first one is I subtract twice x from y and I get -5. So twice x subtracted from y, I get -5. I can change that around to make it y is equal to 2x minus 5. That's the same equation. And the other one, I subtract 7 from y and I get -x. So I subtract 7 from y and I get -x. Rearranging that, I get y is equal to 7 minus x. Next, we calculate the ordered pairs, then plot the points on the same coordinate plane. The answers are that point where the two lines intersect. Now, remember, for straight line graphs, you don't need all these points. You need a minimum of 3 points to plot a straight line graph. But the more points you calculated in the table, you may actually see the answer in the table. Let me demonstrate. Because I'm using a software program to get these points, Excel, it's fairly easy for me to do this. But if you look down here, notice at 4, you have a 3 here and a 3 here. So if you had all those points, you already know what the answer is based on this table that you are going to plot. It is x is 4 and y is 3. But let's go ahead and plot the points and derive the points. So we plot the graph and we get this. This is y is equal to 2x minus 5. That's that one. And this one here is y is equal to negative x plus 7. Okay, I have it as 7 minus x. The software change it around and tell me it is negative x plus 7. Same thing. So what is the answer? The answer is this point here, which is 4 on the x-axis and 3 on the y-axis. 4, 3. So that's the answer to those two simultaneous linear equations. Of course, we need to test them. In the first equation, y is equal to 2x minus 5. If y is 3 and x is 4, we get 3 on the left-hand side is equal to 3 on the right-hand side, which is true. So it works in that equation. Let's try the next equation. Y is equal to 7 minus x. Y is 3. X is 4. And so we get 3 on the left-hand side is equal to 3 on the right-hand side. And so we know our answer is correct. This is the correct answer. So we finished with that one. Now we are dealing with one example of this, a linear and a quadratic function. They are still equalities, not inequalities. And then, of course, we will do one from here and one from there and one from here, mainly review. So this is example 2 for this video. Your company is going to make frames as part of a new product it plans to develop. The frame will be cut out of a piece of steel, and to keep the weight down, the final area should be 30 square centimeters. What should be the width x of the metal frame? That's a question. At first reading, it may look difficult, but don't worry. It's not as difficult as it seems. So make a little drawing. This is the frame you see here. The inside of the frame is 10 centimeters by 5 centimeters. That is the part, this is the part that you cut out from this original shape here. So your question is, what is the width of this frame here? All wrong. What is the width? One width. What is it? That is what we want to find. Well, first of all, let's find the area of the steel before you cut it. So you have 10 centimeters here, from here to there. You have x here, and you have x here. So the length will be 10 plus 2x. The width will be 5 plus this x here, and that x there. So it will be 5 plus 2x square centimeters. And you expand that, and you get 4x squared plus 30x plus 50. Now you could see your quadratic equation there. The area of the steel after cutting. Well, if this is before cutting, and you are taking out 10 by 5, which would be 50, 10 by 5, which would be 50, then that 50 goes, and you are left with 4x squared plus 30x. That's the area of this blue shape. So what do we do with that? For the x-axis, which is the domain, the independent variable, we will use values from negative 10 to 3. But really, all we need is from 0 to 4, because at no time will the width ever be in the negative value. But I'm using -10 so you could see the quadratic equation. And of course, the y-axis, which will be range, it will be dependent variable, will be the area, and that doesn't change. That is always 30. So we get some points. Remember, I said we are beginning at -10 and we're going to 3. Truth of the matter is, we don't need all of those. The width will never be negative anything. But we will use it just so you could see the parabola from the quadratic equation. And this is what we get. That is the quadratic equation. Remember, as I said, you really don't need this part over here. The width will never go into negative value. So really what you need is this first quadrant over here. And our answer is where that area of 30 intersects this graph here, which is this point. Okay, let's see that a little closer. We want the width of the frame, which is x. So we want the reading on this x-axis. Now, the sensitivity here, okay, that is 2. We have 5 divisions. So the sensitivity here is 0.4. So that's 0.4, 0.8, 1.2, 1.6, 2. This point here falls a little past 0.8. It didn't reach 1. But the software I am using can only fit that arrow at 1 or 0.8. I'm not able to adjust it to get between there. So we are going to guess that as 0.9. So the approximate width of the frame should be 0.9 centimeters. This is our answer. That was example 2. So we did one example like that, one like this. That one was new. This one, linear function. This is now inequality. Solve 2 linear inequalities graphically. We did this example before. I am just going to do it over here for those of you who may not have seen it before. Then, of course, we have to do linear programming and speed time graphs. So this was example 7 in video 14 in the same section. Right now, I am using it as example 3 for video 26. The identical problem. No changes. It says, I think of 2 numbers, x and y. If I double x and add 1 to that, my answer is greater than y. Notice it is equal to. If I multiply x by -2 and add 6 to that, my answer is less than y. So remember, we are looking at 2 linear inequalities. Now, by use of a graph, show the region that will meet the requirements for x and y. So we derive our 2 inequalities. We double x and add 1, and that is greater than y. So 2x plus 1 is greater than y. Okay? That's the first inequality. And the next one, I multiply x by -2, multiply x by -2, and add 6, which is this 6. And my answer is less than y. Less than y. So we have the 2 inequalities. So let's flip these 2 inequalities around to begin with y on the left-hand side. Well, think about it. If 2x plus 1 is greater than y, then y must be less than 2x plus 1. So y is less than 2x plus 1. And again, if -2x plus 6 is less than y, then y must be greater than that. Okay, now we have this in something that we can easily recognize and work with. Let's continue. These are our ordered pairs. This would be the domain value, the x value. And for that equality, notice equality, this would be the y value. And for this one, this will be the y value. For example, 1, 3, and then 1, 4. So we plot those two on a graph. Now notice we are using solid lines, which we should not use. We will correct that in a while. So yes, you know how to solve these two simultaneous linear equations graphically if they were equations. If they were equations. But we are not dealing with equations here. We are dealing with inequalities. So we have to adjust these lines. We have to adjust those lines to make them non-solid lines. It will be broken lines, dashed lines. And then we have to choose one side of each one. So we will modify this to show them as inequalities. Now I'm just using 4 points rather than all of those points we had before. For this equality, you will get this if we were using the equality, but since we are using an inequality, we do not include a solid line. So now we have to decide which side to shade. Let's choose this point here, which is -2, 5. We substitute that in the equation under consideration, the inequality, 5 for y and -2 for x. And we find that we get 5 is less than -3. That obviously is false. So this side here, we cannot use that. Let's try the other side. Try 2 and 1. 2 here and 1 there, this one. So 1 for y, 2 for x, and we get 1 is less than 5. That is true. Therefore, we will shade this side over here. This side over here is correct. And if we do that, this is what we get. So this shade part here, going all the way out there as far as you could go and coming all the way down here as far as you could go, represents this inequality, y is less than 2x plus 1. Any point there. So we have that. Let's deal with the next inequality. I'm just using 4 points here again. This is the equality, but remember we are dealing with an inequality. So we plot the equality in dashed lines or broken lines, which is what we have here. That's because it didn't say greater than or equal to, it just says greater than. So now we have to decide which side to shade, that or this. We have to decide which side to shade, the lower left or the upper right, lower left or upper right. So we will use 2 test points in the next slide to determine which side to shade. So let's use this one here, which is -3 and 5. We will substitute that, 5 for y and -3 for x, 5 for y and -3 for x. When we work that out, we get 5 is greater than 12. Obviously, that is false. So any point on this side would be invalid. Let's try the next side. Let's try that point here, which is 2 on the x-axis and 10 on the y-axis. That is to say, when x is 2 and y is 10. When x is 2 and y is 10, we get 10 is greater than 2. That is true. So we will use this side. So anything on this side here, to the upper right, going that way, and shaded here, any point in there, excluding the graph, which is in dashed or broken lines, would satisfy this inequality. Okay, let's put those two together to solve both inequalities. So now we have the two of them together, put them on the same graph. You get this dashed line, so it's not equality. We are not dealing with the equal part. We are just dealing with the inequality part, less than or greater than. And we know this part down here already, we just saw that. We know this part up here, we just saw that. Now look at this area here. This is the required region or area. This part here, going all the way out there to infinity. So I think of two numbers, and whatever I do with the numbers and so on, any number, any two numbers, x and y, in here will satisfy those two inequalities. Let's just try one. Let's try 4 for x and 5 for y. If we do that, 5 for y and 4 for x, we find that 5 is less than 9, which is true. And if we do the same thing in the next equation, 5 for y and 4 for x, we get that 5 is greater than -2, which is also true. So we know that that point there is correct, and we can assume that all the other points in that common area there would be correct. And that served as a preview or an introduction to linear programming, which is what we will consider next. So we finished those three. We are now here, linear programming. And then, of course, we still have to do speed time graph. This was example 4. So we are revisiting this. If you didn't see it before, then this will be new to you. But if you saw it before, it will be just a review. We did this in objective 15 in this same section. And the question goes like this. For a camp of up to 120 children, 2 types of tents are available for hire. The larger tent sleeps 8 and costs $30 per week. The smaller tent sleeps 5 and costs $14 per week. The total number of tents must not exceed 20. Total funding for rental of tents is no more than $420 per week. Your task is to find the number of each type of tent that the camp can get at the funding available to accommodate the expected campers. Now, you see this up to 120? That is a bit tricky. And I'll explain that as we go along, because you may have a true statement that doesn't satisfy what we are looking for. So this is the objective function. We want to find how many tents of each type. And these are what are called our linear constraints. 8L plus 5S must be able to accommodate at least 120 campers. And 30L, that's the cost for the large tent, plus 14S must be equal to or less than 420. We can reduce that to plot the graph, but when we test our answer, we will go back to this original. And then total number of tents, L plus S, because L is the number of large tents and S is the number of small tents. So when we add L and S, we must get no more than 20 or less. So we choose L as the x-axis, get some numbers like 0 and 4, some random numbers. We go up to 20, from 0 to 20. And we calculate the S value for this equation, we calculate the S value for that equation, and we calculate the S value for that equation using these domain values. So we get some points, and we will plot those points on a graph to the best of our abilities, which would look like this. This one here is that. This green one here is that, and this blue one here is that. I don't think CSEC will ask you to actually construct such a graph in an exam. They may ask you to interpret it, though, given such a graph. Now, we want to find the number of each type of tent that the camp can get for the least amount of money within the available funds to accommodate the campers. So we now need to shade the area that is common to all three inequalities, which is this area here. And this area here is called the feasibility area. We will now consider all 5 corners of the feasibility area, all 5. This one here, that one up there, this one down here, this one here, and this one down here, to see which one works best. So obviously, if we try the first point here, A, which is 0, 0, that has no meaning. You will not rent 0 large tent and 0 small tent. Has no meaning. So let's try the next one. Let's go up here. Let's try 0 large tent and 20 small tents. 0 large tent and 20 small tents. That will accommodate 100 campers. We want up to 120. Now, even though this statement here is correct, 100 on the left-hand side is less than or equal to 120. That is not correct for our purposes because we want to accommodate up to 120. So that is out. That will not accommodate all the students. As it relates to money, 0 large tent, 20 small tents, we are spending $280 out of the 420 that we have. So that is fine. And in terms of tents, well, we have 20 tents and we are allowed up to 20 tents. So this is okay. Our problem is here. We have a problem there. We cannot accommodate the 120 campers that we need to accommodate. So it seems we can't use that. So let's try this point down here. 14 large and 0 small. 14 large tents and 0 small. We have the same problem that we had up there. Now we can accommodate 112 campers, but we need to accommodate up to 120. So obviously we have a problem here. Even though this statement is correct, 112 on the left-hand side is less than 120. That is not what we are looking for. As it relates to money, 30 times 14, which would give us the $420. So we have spent the $420, which is what we have. That is fine. As it relates to number of tents, we have 14 tents and we are allowed 20. This is fine as well. So we have a problem there. Let's consider those 3 together on a table. As we said, we have a problem here. We have a problem here. This is fine. That is fine. That is fine. That is fine. So A, B, and C, those 3 corners that we considered so far, on the axis will not do. Generally, your answer is one of the other 2 points that are not on the axis, that are not on any of the axes. So now we still have to consider this point here and this one here. Let's try this one. 7L, 7 large tents, and 13 small tents. Let's put that in the equation. So 7 large tents and 13 small tents, that will accommodate 121 campers. And you may look at this and you may say, that statement is wrong. But you know, that wrong statement is what we want to be right, because we want to accommodate at least 120. If we have space for one extra, no problem. So this wrong statement is the right statement that we are looking for. As it relates to money, 30 times 7 plus 13 times 14, we would have spent $392 of our 420 available dollars. That is fine. And as it relates to number of tenths, 7 plus 13 would give us 20. We are within our limit of equal to or less than 20 tenths. So this seems okay. Put it in the table here. 7 large tenths, 13 small tenths, we can accommodate up to 121. We want to accommodate 120. So this is fine, even though, as I said, this statement here is wrong. But that wrong answer is what we want. We spent $392. We had 420 to spend. We have 20 tenths, which is allowable. So that seems to work. Let's try the next one, though, and see if we get a better deal. This one here, which is now 11 large tenths and 6 small tenths. Let's try that. 11 large tenths, 6 small tenths, we can accommodate up to 118. Okay, so we have a problem there. Remember, this statement is true. 118 on the left-hand side is less than 120, but we are not looking for a true statement. We are looking for a false statement here. Generally, it must be equal to or greater than 120, which would give us the correct answer. And as it relates to money, we 11 at 30 and 6 at 14, we spent $414 out of 420. Okay, we're just within our limits. And as it relates to tenths, 11 plus 6 would give us 17. That's fine. We are allowed up to 20 tenths. So the question now is, so which would you choose if you were in charge of this component of the camping plans? Or in a math class, which is the correct answer? And obviously, the correct answer is D. Please do not reason here that all the campers may not turn up. You have to cater for up to 120. And do not think that if all the campers turn up, you will take those 2 extra and put them in the larger tent, 1 each. That may not be according to regulations. Plus, you may be breaking some laws. Plus, if there is an emergency or like a fire breakout or a flood, and 1 child dies, you probably are going to jail for not following the regulations. So our answer is this. So we finish those 4. We are now here, speed time graph. We did speed time graph already in the last video and the previous one to that, 24 and 25. In 24, we had to draw the speed time graph, and in 25, we had to interpret the speed time graph. This was a question we had previously. We had to draw the graph and then find some things based on the graph. So what I will do is I will modify this question up here, change up a few numbers, and we'll go through the same steps again. So the new question is, a car accelerates from rest to 8 meters per second in 5 seconds. It retains this speed for 15 seconds. It then again accelerates to 16 meters per second in 10 seconds. It retains this new speed for 40 seconds. The brakes were then applied and the car came to rest in 5 seconds. First thing you have to do, draw a graph to show this journey. Assume all accelerations are constant. And then you have to calculate the acceleration during the third part of the journey based on the graph. And then using the graph, you have to calculate the distance traveled during the first 50 seconds. And finally, you have to calculate the average speed during the first 50 seconds. This last part here is easy because if you get the distance, the car traveled in 50 seconds and you know it is 50 seconds, you just divide the distance by the time and you will get the average speed. So generally, only the first quadrant is used with time t on the x-axis and speed v on the y-axis. You add up all the time stated in the question and scale your x-axis appropriately. And then you consider the highest speed and scale the y-axis to that highest speed. And then you plot the points and draw the graph. So if we add up all the time, 5 seconds up here, plus 15 seconds, plus 10 seconds, plus 40 seconds, plus 5 seconds, we get a total time of 75 seconds. That is what we'll have to plot on the x-axis, maybe a little more, 80 or 90. The highest speed we have here is 16 meters per second. It did start from 0. It went to 8, then it went up to 16, then it came down back to 0. So the highest speed is 16. So we will scale the y-axis to 16 meters per second, maybe 18 or 20, a little more. So here are our ordered pairs. This is the domain. That's the range. This is what the graph looks like. Time here in seconds, and we went up to 80 seconds. We needed up to 75. And speed here, we went up to 18. We needed up to 16. So, okay. And then we plot the points. Remember to use small x's or a dot with a small circle around it, not a fat dot. CSEC does not accept that. And so we join the points and we get the graph. That's the first part. Second part of the question says, calculate the acceleration during the third part of the journey. Okay, on a speed time graph, the gradient of any part, if it's a straight line, or point, if it's a curve, indicates the acceleration of the body. So if you look at this graph, you have acceleration here, you have acceleration here, you have negative acceleration here, which is deceleration. You have no acceleration here because it is traveling at constant speed, 16 meters per second. You have no acceleration here because it is traveling at constant speed, 8 meters per second. So let's call this first part here A, this second one here B, that one C, that D, and this over here E. What you want to find is the gradient at C. C is the third part of the journey. That's what we want to find, the gradient. Recall, gradient is increase in y over increase in x. Y here is speed, x is time. So we draw a right triangle there. Our increase in speed, we're at 8 here at this point for that part of the graph, and we ended up at 16. So our increase in speed would be 16 minus 8, 16 minus 8. And our increase in time, we're starting here, which is 20, and we are ending up here, which is 30 first. So for that part of the journey, the time is 30 minus 20. And so you get 8 meters per second divided by 10 seconds. And so you get 0.8 meters per second, which is 0.8 meters per second squared. So that is the acceleration during the third part of the journey. Now calculate the distance traveled during the first 50 seconds. Not the whole journey. The whole journey is 75. So we want to go up to here. We will ignore this part over here. Well, we're not asked about that, so we'll ignore that. So we divide this shape that we have into manageable, simpler shapes. So we want to find the area. Notice area is in quotation marks. indicated by each of these sections. A is a triangle, so that is easy to find. B is a rectangle, that is even easier to find. C is a trapezium. Now, you may not remember how to find the area of a trapezium. So let me remind you. You find half of the parallel sides and multiply by the distance separating them. In other words, you add the green line, the red line, divide by 2, and then multiply by this distance. Now, just in case you're wondering why you do that, essentially what you are doing is you are cutting off that tip of that triangle there, and you are flipping it down here. So you are taking that piece from up there and you are rotating it down here. So now notice you have a rectangle here, and the height of the rectangle is 12 and the width is 10. You are actually converting that trapezium into a rectangle and making it easier. And then, of course, this is a rectangle over here. So let's do this. A, the base, notice I said base is 5. That is to say, from here to here is 5. And the height is 8 meters per second. That is from here, that blue line. And I am using base and height in quotation marks. And when we find the area, half base times perpendicular height, notice that per second cancel out that second and you are left with length, linear. So you get 20 meters. So although we are saying area, our answer is really a linear unit, 20 meters. That is the distance the car would have traveled during that first 5 seconds. Same thing applies for B. It's a rectangle, 15 by 8. From here to here is 15, and from here to there, that green line or the blue line is 8. Multiply those two things and you get 120 meters. You are finding the area, but you are not writing square units. That second cancel out that per second and you're left with meters. So the area, which is really the distance, is 120 meters. Now this shape here, as I just explained, is a trapezium. The distance separating them, the base here from here to there, is 10. One side is 8 and the next side is 16. Well, you will add the 8 and 16, divide by 2, which in effect give you a rectangle of 12. A rectangle of 12, this rectangle here. Because you took that piece up there, flip it around and put it in here. And so you multiply those, half of 8 plus 16 multiplied by 10, and you get 120 meters. That's the distance the car traveled during those 10 seconds there. And finally, this last part here is a rectangle. From there to there is 20. And the height here, this black line, is 16, as you could see over here. Multiply those two and you get an area, which is really a distance of 320 meters. Well, all that remains now is to add the 4 distances. And you get distance is 580 meters. So that is the distance the car traveled during that time, the first 50 seconds. Finally, you want to calculate the average speed during the 50 seconds. Well, you already calculated that the distance was 580 meters. Now, if you didn't do that before, you would have to do it now. But we already did that. Average speed is equal to distance divided by time. We know the distance is 580 meters. We know the time is 50 seconds. You divide 580 meters by 50 seconds and you get 11.6 meters per second. CSEC may accept that. You don't have too many significant figures. You do have more than what is required, but not a whole lot more. If you want to fine-tune that, you could say 12 plus or minus 0.5 meters per second. Right now, you are dealing with two significant figures. Your answer really should have 1, but that is like an overkill. Because if you take 1, you will have to round off at that point, at the 10th position. And so you are going to get 10 plus or minus 5. So the spread here is really from 5 to 15. That is too much. You could leave it like that, or you could even do this. Either one would be acceptable. This one, while technically it is correct, it looks like an overkill. So let's leave that one out. So as I said, most of those may have been reviewed. Some of you may have seen that before or not. We looked at one example each. Solve problems involving graphs of linear and nonlinear functions. So that brings us to the end of video 26 based on objective 26 in section 7. And that brings us to the end of section 7 as well.